Hello.
All right, so good evening, everyone. My name is Alvin Chin, and I am the chair of the ACM Chicago chapter. So welcome everyone to this webinar that we have this evening on cinematic scientific visualization, where science meets Hollywood visual effects. This particular webinar is also in conjunction with IEEE Computer Society, Chicago chapter, as well as the Mid-America IT Connect Club. So we also welcome the members from those organizations. So thank you for joining us here today. So tonight we have our speaker, who is Kalina Borkiewicz. Hopefully I pronounced that correctly. So she's a senior research programmer at the Advanced Visualization Lab.
You can't talk.
Sorry, can the panelists mute themselves? Thank you. So she's a senior research programmer at the Advanced Visualization Lab at the National Center for Supercomputing Applications, NCSE, at Urbana-Champaign. So a little bit about ACM Chicago, if you're not familiar with the chapter. So ACM is the, sorry, if there's someone there, can you please mute? Okay, so ACM Chicago is the Chicago chapter of the Association for Computing Machinery. So if you're not familiar with ACM, they organize conferences, like for example, SIGGRAPH, of which Kalina did a talk in. And we also hold monthly meetings on topics that deal with computing. So I'm the chair. That is my email address if you have any questions or any particular topics that you want to see for future webinars. We have our vice chair, Mark Temkin, who will be introducing Kalina after I finish, and our treasurer, Greg Newmark. If you want to see what our latest webinars are, you can go to chicagoacm.org. And of course, you've probably heard about this from our meetup group. So that's where you will find our latest and past webinars and meetings. And we're also on Facebook, Twitter, and LinkedIn. So this presentation is going to be recorded, and the slides will be made available after the webinar. We also like to thank as well IEEE Computer Society Chicago as well. So they're like a sister kind of chapter to ACM, and we do a lot of joint meetings together. So I'm also the chair as well of this organization, and you can see our web, Facebook, Twitter, and LinkedIn if you want to keep up with us. And also as well, we have Vijay Konkamala, who is the chair of the Mid-America IT Connect Club. So the Mid-America Club is a private social club in Chicago. It's on the 80th floor. So you've gone to the Aon Center. It's on the 80th floor there. It has beautiful panoramic views of the Chicago skyline. And they hold IT club monthly meetings. And so we've done also a lot of joint webinars together with Mid-America IT Connect. And you can see the web, Facebook, and Instagram if you'd like to know more about them. Okay, and with that, I'm going to hand it over to Mark to introduce Kalina.
Hi, everyone. From the Advanced Visualization Lab of the National Center for Supercomputing Applications at the University of Illinois, Champaign-Urbana, ACM Chicago presents Cinematic Scientific Visualization, where science meets Hollywood visual effects. Please welcome Kalina Borkiewicz.
Thank you. It is a pleasure to be here. Pulling up my screen now, just a second. Wonderful. Can everyone see my slide? I'll assume so. Okay. My name is Kalina Borkiewicz. I'm a senior programmer at the NCSA. I'm going to talk to you about cinematic scientific visualization. You've probably heard all three of those words before, but maybe not all together. So I'm going to take just a minute to explain what they really mean. Visualization is the process of converting data into images. And within that, there are a couple of different subfields. So the one that I'm not going to talk about is maybe the one that's most familiar to most people, and that's information visualization, which involves creating charts and networks and 2D graphs that show relationships between data points. So If this value goes up, this value goes down, that sort of relational data, which is different from scientific visualization that involves visualizing data that is inherently spatial. So data that takes up 3D space. Things like galaxies and tornadoes and ocean currents, molecular structures, things that have X, Y, and Z positions, or sometimes just X and Y positions. Within that, there are also a couple of subfields. There's traditional data visualization, where the focus is on data analysis. So this is often done by scientists and for scientists who care about what the data values are, what's changing, and by how much. By contrast, cinematic visualization focuses on science communication rather than data exploration. And we communicate to all kinds of audiences, which includes an 8-year-old kid that goes to the museum with her grandparents, and we want that kid to walk away thinking, man, science is freaking cool, and maybe I want to be a scientist when I grow up. But our audience also does include those grown-up scientists who have spent 30 years studying their fields and expect to see scientifically rigorous data visualizations, which is what we create. Cinematic scientific visualization focuses in equal parts on the science, the art, and the technology to create the images, putting perhaps more of a focus on the art than traditional scientific visualization. I'm part of a group called the Advanced Visualization Lab, and we're about a 50-50 split between designers and programmers. And we work very closely with the various science teams to create data visualizations that are at a resolution and quality that's suitable for TV, for films, planetarium domes, IMAX screen theaters, and other such public-facing venues. So here's a sampling of some of the venues that the team that I'm part of has contributed to, with this subset being the ones that I have personally been involved with. I'm going to play a brief demo reel that shows off some of the work that we have done. Creating these sorts of visualizations involves quite a complex pipeline that I am not going to cover in detail, but that I will simplify by saying that it involves solving 3 types of overlapping challenges. I'll go through all of them, starting very briefly with the issue of science communication. I love this comic because I feel like it explains this issue rather well and in a funny way. So we're living in an era of misinformation and fake news. Whether or not the media is lying to us is up for debate, and I'm not going to go there. But the fact of the matter is that communicating a new piece of scientific information to a broad audience with different ages and different cultural backgrounds, different levels of education, is actually a really, really hard problem. And it also turns out that sometimes there really just is no good way to explain something. Let's take map making, for instance. Sometimes it's not practical to show the Earth on a globe and you want a 2D map representation. That's, a common thing. The Mercator projection is one of the most common ways to do that, and that looks something like this. But it misrepresents the size of land close to the poles. So here's a piece of web-based software where you can drag around different countries and see what they would look like on different parts of this map. So Greenland would be very different depending on where it is. So it's not a very accurate visualization, is it? Let's try a different one. Here's a projection that solves that problem. Now everything is the correct size, but clearly we've introduced a new problem. Now Greenland is split in half, which is not optimal. And you can't exactly take a ruler to this map and measure distances. Surely there's a way to solve both of these problems though, right? Well, it turns out no. There are many, many different ways to visualize the Earth in 2 dimensions, and all of them are wrong in one way or another. So there's this really wide gap between numerical information and how we can display and interpret and understand that information. Projection issues aside, maps are a great way to present and display information. Here's a map where each state is colored by which party took most or all of its electoral votes in the 2016 election. And at a glance, it seems like America was split pretty evenly between red and blue. But the amount of red ink on this map isn't proportional to the amount of electoral votes that went to the red party. It's proportional to the geographic size of each state. So Montana adds a huge amount of red ink for only 3 electoral votes, while the relatively small New Jersey adds a whopping 15 votes to the blue party. Here's a recreation of that map that scales the size of each state based on how many electoral votes it gets, and you see a more accurate result of the election. We can do the same thing by county rather than by state. And now this data visualization tells a different story than just who won the election. It tells the story of how urban areas dominate the outcome of elections. Or a different narrative you could tell with this image is that the country is deeply divided and there's people with very different views living right next door to each other, right? Well, no, not if we color them by the strength of a party's dominance. Here we can see that there's a lot of purple and not so many things that are strictly blue or strictly red. So maybe we're not as deeply divided as the other images would suggest. It should be becoming clear that data can be visualized in a variety of different ways to tell a variety of different stories. And you can easily spin a data set to tell the story that you want it to tell, whether on purpose or by accident. Some visualizations are simply better than others. Every visualization that you see, someone has made some kind of decision on what to show, what not to show, and how to show it. If there's one thing that I want you to take away from this talk, it's that there is no such thing as a purely objective visualization. These 4 images show the exact same colliding galaxy data set at the exact same moment in time, but they are very different. In A, we're looking at just the stars in the data set, and we're emphasizing new star growth. In B, we are again looking at just the stars, but we are emphasizing the direction in which the stars are moving by adding motion blur. In C, we've added gas, and the gas is colored by the identity of the originating galaxy that the gas came from. And in D, we're again showing stars and gas and coloring by where the gas ends up rather than where it started. So each of these representations uses the same data to tell a different story. Now that was an innocent example, but they aren't always that way. The story that you tell with the data doesn't necessarily even have to be true, even if the data is true. So can anybody tell me what is wrong with this visualization? I want you to type into the chat what your guesses are. Don't be shy. I wanna see what you guys think. Great first answer. Damien says it's upside down. Yes, so the y-axis is upside down here, which means that gun deaths look like they're decreasing when they are actually increasing. And there's no way to know if this visualization was made maliciously to lie to people about gun violence, since that's a politicized issue, or it could have simply been an honest mistake where someone just wanted to make a cool looking graph that is unique. But does it matter what the intent was when the effect is the same and it gets seen by thousands or hundreds of thousands of people? To make sure that our visualizations are as accurate as possible, we work really closely with the scientists and we involve them in our iteration process. I personally am not a scientist, I'm a programmer, but I visualize molecular biology and astrophysics and atmospheric sciences and all of these things that I am not an expert in. and I don't pretend to be. So working with experts can help identify inaccuracies a long time before they make it into the visualization, and can validate that the decisions you're making convey the science as accurately as possible. I'm not going to say accurately because arguably that is not possible, but you want to convey it as accurately as is possible. We don't just talk to scientists, we also talk to our audiences. We identified recently that our audiences sometimes have trouble telling apart the difference between photorealistic data visualizations and photographs from telescopes, or purely artistic illustrations. So testing our audiences and interacting with them helps us identify these problems and work on solving them. So let's move on to design challenges. We recently worked with this data set of an organelle called a chromatophore, which does photosynthesis. And this here is a visualization that the scientists had made a couple years before our collaboration. And the intended audience for this video is other scientists. So it's on a white background so that it can easily be put into PowerPoint presentations. And it has labels with vocab words that I wasn't familiar with when I first looked at it. So what we wanted to do was to take this same data set and tell this exact same story, but to make it exciting and immersive and understandable to everyone, not just scientists. So we started out by creating a context. We made millions of copies of this chromatophore and organized them into the shapes of the bacteria that they are found in. We designed this exciting camera move using our custom camera choreography software called Virtual Director, which we linked together with VMD, a scientific software for rendering molecular structures. We changed scales and we slowly increased the amount of detail that we showed to the viewer. So now we transitioned into an X-ray view where we can see inside this chromatophore and see all of the detail within it. We don't just show a data set, we design an experience that includes cinematography, lighting, color, moving elements, and tells a story. So we just saw a photon of light hit the chromatophore, and now the process of photosynthesis begins. I'm not going to play this whole visualization because it is quite long. We end up diving into the chromatophore and then back out and see ATP being created. And it kind of feels like a roller coaster going in and out, and it's a lot more immersive than the first video that I showed. So one of the things that's really important about what we do is providing context for data. Here is a visualization without context. So we're just showing a single data set. Does anyone want to take a stab at guessing what this is showing? Please use the chat. It kind of looks like an orange, maybe. It is not that. The corona, the sun, sun cycles. Nice, you guys are good at this. Yes, we are looking at the inside of the sun. Hopefully that should become a lot more clear if we show it like this. So now we are flying on the outside of the sun, and then we dive underneath the surface and we see these rolling waves of plasma. This is also really exciting if you watch it in the documentary. It's narrated by Benedict Cumberbatch, who does a much better, more exciting job of talking about it than I do. But a challenge in providing context is that it requires combining multiple different data sets. And each data set is created by a different science team. Scientists tend to focus on one small piece of a puzzle, like just the inside of the sun and not the outside. So we have to combine these data sets from different science teams, which are in different data formats, different resolutions, different time scales, and each one has its own problems that we have to figure out how to solve. So for this single frame, let's break down what kind of data sets went into it. We began with a data set of surface convection by a scientist named Matthias Rempel, and this data included surface magnetism vectors, which we rendered as these spikes. The sun's surface was a simulation by Dr. Rempel, and that came to us as a series of black and white rectangular images. We tiled these images and mapped them onto a sphere, and we tiled each of the tiles. We started playing at a different moment in time and blended between the edges of each tile so that they wouldn't look like repeating patterns. And what I'm showing here is actually an earlier draft where we do see some edges here that we did end up fixing, but ignore those for now. They weren't there in the final version. We then used a facing ratio render layer to make the sphere more transparent, where it's facing the camera. Around the rim of the sun, we used photographic time-lapse imagery from NASA's Solar Dynamics Observatory, which is a space-based telescope that has several different cameras looking at the sun. We put the whole sun in the correct context. This might be a little hard to see over Zoom, but we added this starry background, which is a photographic mosaic from Axel Mellinger. And the interior simulation is by Mark Nish and Nick Nelson, and it shows this important feature of the interior of the sun, these spinning vortices around the equator that the scientists nicknamed bananas, which I find hilarious. Here is a visualization made by the scientist where you can see these solar bananas around the equator. And we also added these rotating streamers around the vortices to really emphasize their motion. With that, let's move on to some technical challenges. The first is that we're working with big data, and what that means keeps changing every year. Big data keeps getting bigger. And that goes for both simulation data that's created on supercomputers, as well as observational data that's collected with sensors like telescopes. What we're looking at on this slide is an early rendering of the Vera C. Rubin Observatory, which is expected to be completed next year, and is going to produce 20 terabytes of data every single day. Here's an example of a large data set that we are currently working with. This data set is a digital elevation model, which is a record of height of every piece of land north of 60 degrees on the entire globe. So that's 1/6 of the whole planet at a resolution of 2 meters per pixel. So that data is 200 terabytes in size, and it took the scientists 1.5 billion hours of processing on the Blue Water supercomputer to assemble and process and put together this data. We aren't working with the whole data set for our visualization, but for this documentary, we are working with 45 terabytes of data, and we've spent 110,000 hours of render time on our local supercomputer just to render the images for the visualization. So hopefully this gives you an idea of the sort of scale that we're working with here. Not only is data big, data is also messy and requires cleaning and processing. Here's an example from the Arctic elevation data set looking at one zoomed in region where an ice cap is collapsing on an island north of Russia. An issue with satellites collecting data about the Earth is that they're above clouds, and clouds often get in the way. So as the data is being collected, you can see these ugly, random, patchy things here that are the clouds in the data set. When reconstructing this in 3D, you can see these awful giant spikes where the clouds are incorrectly mapped as elevation data. We were able to clean and process this data with a combination of a first pass of algorithmic cloud removal, followed by manual labeling and masking, and finally using machine learning to do segmentation and automatically creating cloud masks. Because data can be so obscenely big, it often isn't practical for scientists to capture or create data at regular intervals. So they usually produce more data when some interesting or exciting event is occurring, like the collapsing ice cap, and less data when there's really nothing happening, nothing changing. This results in data sets where time might not move linearly, which can't produce smooth-looking visualizations without additional processing. Here's an example of that. So this is a early look at a planetary collision that we received from a scientist, Dr. Robin Knupp, before we put in any design work. Obviously, it's not very pretty to look at. It's just gray points on a black background. But aside from that, there are some things that are a bit disturbing about this video. One is that it's over really quickly. Things happen so fast that it's hard to even get a sense for exactly what is happening without watching it over and over a few times. And another issue regarding time is that the video seems to speed up right about then, right about halfway through there. So it does look a little off. Here's the final visualization that we made with this data set. We added lighting from the position of where the sun would be, which gives depth and shadows and textures to the planets and a background of stars. And we used information from the data points, taking the type of matter and the temperature at each point to determine if the point should be a solid, liquid, or a gas at any given moment. When a point becomes hot enough to be a liquid or a gas, we also make it emissive, so we make it light up. We slowed down the simulation by quite a lot to make it so that you can actually sit back and watch and enjoy it. And perhaps one of the most important elements that makes a video look and feel cinematic is the camera treatment. So we are very slowly revolving around the data, and we get right up close to the action to make it immersive and to convey the really large size of these planets. This was actually created for a planetarium dome. So when that ball moved in front of you, it was actually, you kind of have to imagine that being extremely large and directly above your head, and it was actually very exciting. Slightly less exciting here, but still looks cool. So I am going to let this video play to its completion. So while it does, I'll just describe what we're looking at here. The real world timescale of this collision is 24 hours. And what we're looking at is a planet that collided with early Earth, and that planet was called Theia, and it sheared away about 1/3 of our planet. Theia's shattered remains enveloped the Earth in a shockwave of superheated vaporized rock, and a molten ring formed around the planet, subjecting it to a rain of secondary impacts. And about 100 years after the end of this video, the orbiting cloud cools and coalesces into a single orbiting body, our moon. And that's just about over, so I'll move ahead. So that was a little bit of a tangent. So let's go back to the data and break down and fix some of the visual problems. So with regard to the timing, why does the simulation speed up halfway through? Time's going at 2 different rates in different parts of the simulation. In this case, there's only 2 rates. Oftentimes, time will speed up and slow down seemingly randomly. So this is actually easier to deal with than some of the other problems. But this particular scientist was more interested in focusing on the initial impact. So she was more interested in the first part of the simulation. So that has more resolution and time. And the second half has less time resolution. So this reduces the amount of time that it took her simulation to run and decreased the size of the output data. So of course it makes sense from a scientific perspective to do this. But in order to be able to effectively visualize the simulation, we do need time to be linear. So we slowed down and retimed the data through an interpolation method called advection, which uses the position and velocity of each point to advect it both forward and backward simultaneously, and take the time-weighted average as its intermediate position. So this is one of many interpolation methods, and we tried a few, and this was the one that worked best, considering that the points do react to gravity in orbit rather than kind of going in straight lines. When dealing with data from physical sciences, whether that's astrophysics or molecular biology or anything physical, objects are often interacting across vastly different scales, and that often leads to floating point errors. And creative methods have to be taken to be able to show both the large scale and small scale objects simultaneously. So something that we'll often do is move the origin of the data, so kind of move our whole scene closer to the origin as we start to get problems, things start to shake and get these floating point errors. And then that requires creating multiple different camera moves and figuring out a way to blend between them smoothly and make the shot appear continuous, even though we're constantly moving the positions of where the origin is. A single data set is very unlikely to have things both at the resolution on the scale of the Earth as well as the entire observable universe. But as I mentioned, it is often useful to combine multiple data sets together to create a compelling story. And a couple years ago, we actually did do a single continuous shot starting at the scale of the Earth and zooming out through the solar system, through the Milky Way to see the large scale structure of the universe. We have seen this image a couple slides ago, and we know that it's problematic in terms of communication and perception, but it's also a challenge from a technical standpoint. Since there are many different coordinate systems that the same data could possibly be stored in, that can be problematic. Many of these data formats might not be natively understood by the visualization software that you're working with. And oftentimes you have to translate between these data formats to get it into an appropriate format for the visualization. That's not only true for maps, it's true for all spatial data, which comes in a variety of coordinate systems and also a variety of data formats. Here are just some of the weirder ones that I have found online. I've only actually ever worked with this one, and I really hope that I don't ever have to work with these others because they do look very challenging. I'm sure they will come up. Another problem is that there isn't actually existing software for cinematic scientific visualization. There's software for cinema, here referred to as VFX or visual effects software. And then there's software for science, but we are kind of in between those two. So we can use either category of tools to create our visualizations, and each type of tool has its pros and its cons. Generally speaking, the visual effects tools provide great controls for things like cinematography, color design and artistic elements in general, but they don't understand scientific data. Those are tools created for artists to use. Whereas scientific software, on the other hand, is created for scientists to use. So it does understand all these weird, complicated data formats, but makes it really hard to do cinematic effects. You don't really get much control over things like camera and lighting and design. We also have some of our own custom software that we have built to solve some gaps that don't exist in either of these categories. And this is a non-comprehensive list, but just some of the tools that we've worked with and are familiar with. One of the custom tools that we use is called Party View, and it's developed by Stuart Levy on our team. We use this for pre-visualization. So the reason that we need to pre-visualize data is that scientific data can, since the files are so large, they can take seconds or minutes to load a single data file in graphics software, and oftentimes we'll have thousands of files because we're working at 30 frames per second. So what we do is sample down the data so that it can fit into memory and so that we can render it interactively. The goal with this is to have just enough information to understand the geometric relationships in the shot and to compose the camera frame. We can also use pre-visualization to dial in a desired data rate to set the length of the scene and then figure out how we want to interpolate and slow it down. Usually we're slowing it down rather than speeding it up because we want things to appear large and cinematic. We use Party View in conjunction with another custom tool, Virtual Director, to design our camera choreography. Bob Patterson on our team is the person that does that, and he uses a space pilot, which you can think of as kind of a joystick, and he literally flies around the data to record a camera path. So here's a recording of Virtual Director. Here, Bob is showing the camera's view at first, and now he is separating from the camera path that he's designed and can see it from the outside. He can turn on a television view so you can see what the camera is seeing as well as what he's seeing from the outside. And he can go in and edit the spline at any key point along the path. And there's a bunch of other features here, all for creating effective cinematography techniques. What makes Virtual Director unique in this field is that it allows Bob to perform a camera move, much like a real-life cinematographer with a physical camera, rather than defining it in a more algorithmic way, like most software requires you to do. So we don't create all of our own custom software. There are plenty of perfectly good tools out there that we can start with as a starting point and then modify and add on to fit our needs. So Houdini is the primary visual effects tool that the AVL has been using in recent years. This is kind of the main tool used in Hollywood right now to do things like make things explode, smoke effects, fire effects, flooding, but we use it for our scientific purposes. Houdini is obviously not built for scientific visualization, but we continuously are adapting it for our needs by writing C++ plugins into it and creating pipelines for data processing that work with the software. So here I'm showing a tornado simulation that we read into Houdini with one of these plugins. It was originally written in a netcdf format, and I wrote a C++ plugin that can interpret that and convert it into a Houdini volume. Here's the final rendering of that same tornado done in Houdini. A problem with working in Houdini is that it expects all data to be in a uniform Cartesian grid if it's volumetric data. However, this is often not an efficient way for scientists to store their data. I mentioned that scientists might only write out certain periods of time where there's exciting things happening, but that's also true for space as well as time. So this tornado data set that I just showed you was in a grid that looked something like this. The tornado itself, can you see my mouse? I think you can. Yes, okay. The tornado itself was in this central area where there's really high resolution. And there were a bunch of clouds off to the sides that aren't very interesting, so those were lower resolution. Here's kind of a different data format that has the same idea, but looks very different. So again, you have resolution just where you want it and less resolution in places that you don't. And this particular format is called Adaptive Mesh Refinement, or AMR, and it's made up of nested multi-resolution grids. Data can also come in a spherical or in a cylindrical grid. A lot of the solar data that I showed a couple slides ago looked like this. And there's a bunch of other formats that don't nicely convert into a uniform Cartesian grid. So if we do want to work in Houdini, what are our options for working with this type of data? Well, we could sample the data and force it to fit into a uniform grid. And there's a few different ways to do that. We could create a uniform grid at this finest resolution, which will retain all of the interesting bits of the data, but is going to waste a lot of resources. We're going to get a huge file out of it, and all of that extra memory is going to be wasted on places like this where there isn't actually anything interesting going on. So rather than doing that, we can use a medium resolution, say this square, and make a uniform grid that looks like that. But in that case, we're going to lose everything that is higher resolution, and that's really the things that we care about. That's where the exciting parts of the data are. So that brings us to option B. We're not tied to Houdini. I mentioned there's this other category of tools. So let's see what working in a scientific tool is like. To just talk about one example, there are many scientific tools. YT is one that we've been using recently, and it is a scientific analysis and visualization Python package. We use it to create this visualization for the documentary Solar Superstorms. And a great thing about YT is that it understands a whole lot of really complicated data formats. So this particular data was in the AMR format that I described that's made up of these nested multi-resolution grids, and YT just understood it. We didn't need to do any translation, any processing on the data side, and that was great. Since YT is a tool aimed at scientists, it comes with a lot of features that are useful to scientists and not necessarily useful to artists, like creating derivative data. So here we have traced magnetic field lines through a 3D volumetric magnetic field, and we were able to do that with just 2 lines of Python in YT. This is something that we can do and we have done in Houdini, but it does take significantly more effort than just a little bit of Python code. YT works in parallel and is installed on the Blue Water supercomputer, which is the one we have on campus at the U of I. And we've taken advantage of this and have been able to run YT across thousands of cores. And we have used as many as 16,327 hours in 1 day of rendering on Blue Waters with YT, which would have come out to over 3 weeks on our local clusters, which is where we do a lot of our rendering, or 2 years on a single machine, which nobody would ever do, but it's still fun to think about. Off-the-shelf general purpose tools can never do everything that you want them to do. And conveniently, YT is open source. And even more conveniently, one of its primary creators, Dr. Matt Turk, is a colleague at the NCSA. So when we were working on Solar Superstorms, we were actually able to bug him and his team to help develop the software so that it was suitable for what we wanted to do with it. So why isn't YT our primary tool? A problem that arises with scientific tools is that they often require some kind of domain expert to be able to even use the software. And in this case, YT is a Python tool, and it doesn't have a graphical user interface. So the required experts are programmers. Typically, when we're working on a project, our pipeline starts with the programmers, myself and Stuart Levy, ingesting the data and creating tools, which we then hand off to the artists and designers in our team. And of course, there's back and forth, but generally that's kind of how it starts and how it ends. But when using YT, the artists can play less of a role, since most of the steps of the pipeline have to be done programmatically. So color maps, camera paths, artistic elements need to either be created programmatically or created in a different piece of software and then exported and imported, both of which require a lot more coding than an artist-friendly tool like Houdini. Another downside is that YT only renders volumetric data. What that means is like this cloudy sort of thing that you're seeing here, which is different from surface data, which looks like these lines here or this ground plane. So YT wouldn't be able to do something that combines these two data sets because YT doesn't do surfaces and only does one thing at a time. So it makes shots like this impossible, where we have a volume integrated with lines and with lighting and shadows, and this would just not work. So we customize these tools. We realized that scientific tools like YT and visual effects tools like Houdini have completely opposite strengths and weaknesses, and neither alone is ideal for cinematic visualization. So what we've figured out is that we can actually create a custom middleware called YTini. I'm really proud of that name. I think it's super cute. We went out for martinis when we published this. But what YTini does is it uses YT as a data reader. It exports an intermediate file format that Houdini can read, and we can do the rest of our pipeline in Houdini. So we really get the best of both worlds. Here's a rendering of an AMR dataset done in Houdini with YTini. Our team had been dealing with AMR data for decades, and this is the first time that we've been able to render it in visual effects software as opposed to scientific software. So on the left is an early attempt, which I like to show because it has these visible lines that show the different AMR grid levels. And on the right is the final seamless rendering with YT. So YT reads the AMR data, exports it in a OpenVDB data format, which is a sparse volumetric format, and then loads that into Houdini. That is a vast oversimplification of how it works. If you are curious about the details, I encourage you to read our 18-page paper in the Astronomical Journal. And with that, I think I am out of time. So I tried to cram in a lot of information here and kept a lot of this at a high level. But I want to mention that this talk was based on a 3-hour course that I taught at SIGGRAPH together with some folks from NASA's Scientific Visualization Studio and the California Academy of Sciences. But that 3-hour course is based on a 4-week course that I developed with a couple of colleagues, AJ Christensen and Jeff Carpenter, and that is available on Coursera. If you're interested in a deeper dive into this subject, though still at an introductory level, you can watch the video lessons for free there. So thank you. I believe now it is time for the Q&A.
Hi. Okay, so we're looking for questions. We have a few already lined up. So we're first going to have a question from Jeff Solon.
Oh, can you hear me okay?
Yeah.
Yes.
Kalina, that was wonderful and awesome, and it is really cool to see all the things that you're doing over there. As you almost kind of answered my question on your very last slide, but my question, well, it's kind of two parts, but one was how can like very early computer science students start messing with some of this stuff? Like if they found it really interesting, it comes across as intimidating because it's really there's a lot going on there. So what's sort of a low floor, wide wall way of getting very early computer science students interested in this? We've done some stuff with processing and using that to do some visualizations. But I'm just kind of wondering about that. And then was wondering about the most common languages that you use. I heard you mention C++ for plugins, but I was curious if that's the dominant language for the kind of work that you're doing, or if there's other languages, Python and R, or if you play in that whole space all over it all the time.
So C++ and Python are pretty much exclusively what I use. Well, a little bit of Bash, if that counts. C++ is mainly for creating entire pieces of software, or for creating plugins into Houdini. And Python I use mostly if I'm doing kind of external data processing. So Ytini, which I mentioned, that is based on Python. So that's kind of the main thing that we've been using lately. As far as how to get new computer science students into it, I did mention the MOOC. That actually assumes no background knowledge of any sort, including no background in computer science. So it really is intended for anyone that's interested in it. We do have some assignments that can be done programmatically, but also don't have to be. That's kind of the best answer that I have for that. If the students are also just interested in different kinds of visualization, like information visualization, that's something a lot of kids get excited about, and that maybe is a good starting point. It often doesn't require gigantic data sets. So, using something like d3.js, JavaScript, you can create interactive websites with different types of data, and that can be very fun as well.
Thank you very much. I really, really enjoyed you talking. It's great to see you.
Also, thanks for coming. Maybe I'll just mention to everyone, Jeff was my high school teacher that taught me programming in the first place. So it's really nice to to have you here.
I'm so proud of everything you're doing. Thanks for sharing this with everybody. It's so cool.
Thanks so much.
Jeff is a past ACM speaker. Our next question is from our treasurer, Greg Newmark.
Hi, yeah, I was wondering just about the steps, like how do you think of a new project? Like, what do you go in a certain order, or do you keep circling back and then like do the parts? Is like the final render always the longest thing, and like, oh, we're going to kick this off and come back in a week? I imagine different projects come out differently. But is it a linear process getting to the end, and then what parts take longer or shorter?
It definitely is not a linear process. Every project is completely different in terms of how we do it and what order it goes in, how long it takes. But sometimes the conception of a project is that, like IMAX or Disney will come to us and be like, hey, we want you to create a 5-minute visualization for this movie we're doing. Or other times we will submit a grant proposal to the National Science Foundation and say like, hey, here's what we want to visualize. So, we always start out with a data set of some kind, or a story that we want to tell, and then we go find the data that will tell that story. But oftentimes, even if we do have a data set in mind, we kind of don't know where that will go. So we always start with pre-visualization to see, well, what is this data actually showing? Because even though you might say like, okay, I know I have a data set of a galaxy, until you actually visualize it or pre-visualize it, you won't know what is actually interesting about that data set. So is it like the supernova explosions, or is it like evolving in some way? So there's a step of data exploration that always has to happen. And then there's a lot of back and forth between, the programmers and the designers going back and forth. We'll read in the data into the software, process it in some way, and then hand it off to the designers. And then they'll say, well, actually, it would be really cool if we could do this to the data, and slow it down. Or if we could maybe extend the edges, or I don't know, all sorts of different things. There's a lot of different back and forth. So it really isn't a linear process. And these things, it often takes months to create a single, like, couple-minute visualization. So I think I touched on the points that you were asking about, but I don't know if I missed something.
Thank you.
Sure.
Our next question is from Eric Friedman of Columbia College. Are there additional tools that you use to add interactivity to create interactive cinematic scientific visualizations?
So interactive visualizations aren't our specialty. We do a little bit of that. And when we've done that, I mentioned, the internal tools that we have, like Virtual Director and Party View, are interactive, but those are kind of for our purposes for creating our designs and choreographing the camera. As far as final visualizations that are interactive, we have used Unity, the game engine, to create visualizations of like old architectural sites that you can walk around through and explore. We have done a little bit of work with Unity with the Arctic digital elevation data as well. So I guess as far as the outward facing visualizations that we make, Unity has been the tool that we use.
Okay, the next question is, in one slide, there was a question about what the rendering was. What was the answer? I think it was about the sun.
Oh, the sun, yes. So it was solar plasma underneath the surface of the sun. So the top 1/3 of the interior of the sun consists of solar convection, is the scientific vocabulary word for that. So that's what we were looking at there.
This is from Herb Schilling. You mentioned how you want to explain science to everyone from 8-year-olds to adults. How do you test that it works with such a large range of people?
So often, if it works for an 8-year-old, it will work for an 80-year-old. Kind of the bigger challenge than the opposite age ranges is kind of the young kids and the experts. Whether the experts are, 25 or 80 is irrelevant. But, like I mentioned, we test our audiences. We show our visualizations to, just vast audiences before they get released, while we can still make changes. And we often incorporate that feedback. Usually it's to change the script rather than the visualizations, because, it just is a matter of explaining it better. But, we change visualizations based on feedback as well, to make it understandable to kids. And as far as making sure that it's understandable and accurate to scientists, we just involve them very closely in the whole pipeline.
The next question is from John Putnam, who is my old prof. I took computer graphics with him, and we wouldn't have this presentation without him. So his question is, what about the audio and music background? Does that enter into your planning?
It does not. It sort of does and doesn't. So all of our visualizations do end up getting a score and soundtrack and sound effects, but that is out of our hands. That's not our specialty. So we'll usually create the visualization, and then once we have that finalized, we'll hand it off to the film director, who then does all the other things, like, finding the narrator and getting the score written, and all the other sort of things that go into making a documentary that are not visualization.
Here's a really good question. I would ask this. How did you get into doing scientific visualizations? Did you stumble onto this, or did you target this kind of work?
I stumbled onto it. So I targeted computer graphics. I thought that I wanted to go into Hollywood and work on the next Star Wars movie, which I didn't end up doing, and I'm actually quite happy with where I am now. It's a lot more satisfying. I'm still doing amazing computer graphics sort of work, but I'm also helping people and educating people. So I did kind of stumble onto it. I had always been interested in astronomy as a kid, so it was a happy combination of computer graphics and astronomy, as well as other sciences.
Okay, the next question is, do you take precautions to limit bias on what should be visualized? This is from Lauren Landwehr.
I'm not sure what you mean by bias. Bias like in the data, or bias in the understanding, or like gender and racial? Because in terms of like gender and racial bias, we do conduct surveys where we ask, how understandable was this? What did you think of it and get out of it? And we do ask demographic information to make sure that we aren't introducing any unconscious bias in that sense, and explaining things in a way that isn't understandable to a specific demographic. I'm not sure if that is what you are asking about. Please submit another question and clarify if I didn't answer your actual question.
Here's another question from Herb Schelling. You mentioned one example of using machine learning to create a visualization. How much of an impact is machine learning having on scientific visualization?
So this is a very hot and new topic. I mean, machine learning is hot everywhere right now, but especially in visualization, it's a little bit under leveraged. That was actually one of the first times that we used machine learning while working on a visualization. So it's not something that we do a lot of, but it is something that has been helpful and is really cool.
Oh, going back to that other question about the real image. It was the real image slide. Asking, was it real? Was it an artist, or was it computational? That was the question.
Let me pull that up. Am I still sharing my screen? I don't think I am.
No, we see you.
I'll pull it up just so everyone knows what I'm talking about. I actually have another slide that I didn't include in this that shows the results of this survey question. So this is a data visualization, and it turned out that 100% of the answers thought that it was at least partly a visualization. So nobody thought that it was purely images. No one thought that it was purely an artistic illustration. So I thought that was a success. Well, actually, the rim of the sun is photographic imagery, and everything else is a visualization. So it is a combination of both. And since we were actually really focusing on trying to, solve this problem of people not understanding, in this case, we succeeded.
And before we close off, I'll ask the final word here. So I heard when I saw your presentation that you would think this would go the other way, but I've heard that a lot of people in Hollywood and games, after they get tired of blowing up zombies and buildings and all sorts of things, they actually find this field more interesting.
Well,
so I thought that was really interesting.
Yeah, I find it interesting too. I mean, it does go both ways. So something that I was really excited about a few years ago is the movie Interstellar. Actually employed an astrophysicist, Kip Thorne, who wrote these amazing papers and theories on how black holes work and how they look. And they actually, created a scientifically accurate black hole for that movie. And one of my coworkers, A.G. Christensen, actually worked on that movie as well. So I hope to see more of that in the future, because why not include real science in movies?
Great. All right. Well, Alvin, let's take it.
Okay.
Thank you again.
Thank
you, Mark, for moderating questions, and thank you, Kalina, for your excellent presentation. Yes, there was a question regarding about the recording, and the slides will be made available. You will see it in your email after this webinar. So I'm going to share my screen here. Hopefully, I think you can see my PowerPoint shared screen here. So we're going to talk about our next meetings that we're having. So we're going to have our last meeting / webinar in December. It's going to be December the 9th, Wednesday, December the 9th, same time at 6 p.m. And talking about machine learning, I'm going to give a talk on machine learning for connected vehicles. So some of the stuff that I've been doing with machine learning and stuff for connected vehicles with BMW. So please stay tuned and attend this meetup. It's already available on the meetup.com/ACM-Chicago. So you can go ahead and you can start to sign up. And the Zoom link for that will be made available shortly. And then to start off our new year for 2021, we have Dr. Mark Bennett. And so Mark, I think you're here on the line. Maybe you can talk about what you're going to be talking about for January.
Sure. So hi, everyone. Mark Bennett with NVIDIA. Can you hear me okay?
Yes.
Okay, so some of you may not know of NVIDIA, and some of you may know of our computer gaming hardware. And it turns out that the advanced computer architecture used for graphics is finding its way into scientific research, autonomous vehicles, and artificial intelligence in general. So I'll be talking about explainable AI as it applies to finance in January. I hope you'll join us.
Great. Thank you, Mark, for being here this evening and for introducing a wonderful, interesting topic on this. So yes, we are at 7:00 p.m. So we are right on time. So again, thank you to Kalina for the wonderful presentation this evening. Thank you to all of you. Thank you to the rest of our panelists that were here this evening. Thank you for attending this webinar. And if you haven't already, I have the polling. So we would like to get your feedback regarding about this webinar to see how we are doing. And with that, I wish you all have good health and be safe and have a happy Thanksgiving. And hope to see you here on a future webinar in December. And take care. Have a good night.
Thanks, Alvin and Kalina. This was amazing presentation.
Thank you so much.
All right. Thank you all. Have a great night.
Thanks. Bye.
Thank you.